Hello, ladies and gentlemen. This is Alice in Beijing. I'm so glad to meet you again on I Can Act Talks. Everyone knows that I Can Act Talks now is already 5 months, close to 5 months. Yeah, we have invited many speakers from worldwide to get on this stage to share the latest work and use their technologies to connect the world and the universe. We are so proud of what we have, this world leading scientists on this stage. So today we're going to have more. Yeah, because today we have two speakers was very wonderful. Was Kuniharu Takei was from Japan. Yi Zhang was from Tsinghua, my neighborhood. And we are so lucky today we have a Professor Saif Rahman who is running for his IEEE president now, and he's going to deliver a talk during the panel discussion time to tell us what he is going to do after if he can win this election. And we have a Professor Ting Zhang be my co-hoster. Yeah, he was a famous scientist, much famous than me. So you will know most of his work, and he's going to introduce Yi Hui later. So today, without further ado, we first will, go to the talk from Kuniharu Takei. Yeah, so this is a very proud moment because we first time has speakers from Japan. We have two, co-hosters from Japan in the previous talks, but this was the first time we have the speakers on this stage. So Kuniharu Takei, why choose him? Because he's the most handsome scientist from Japan. I do think so. I read most of his papers, and he's doing a lot of nice work for the flexible sensor and the circuit, and also some are very famous application in the IoT. And he won a lot of awards. Though he's very young, but he already won a lot of awards. I couldn't remember all of them here, but I remember some Young Scientist Award, Young Professor Awardship, and some very interesting like Max, award. So yeah, he's really a big star in Japan in the flexible sensors and circuit. Today he's going to talk us some story about his work in this field. I have a wonderful slides he will going to share you. Okay, Kenny, are you ready? Yeah. So
yeah.
The word is yours, the stage is yours, please.
Well, thank you very much for the introduction, Alice. So, hello everyone. So, my name is Kuniharu Takei. I'm from the Osaka Prefecture University, Japan. So, actually, I didn't know I'm the first speaker for this I Can X talk from Japan. So, I'm great honor to be the first speaker. So, first, so today, so I want. What? Really? Can you hear? Or can you see that? Sorry. Okay. Okay. So today I'm going. Yeah, good. Okay. So today I'm going to talk about our recent progress about the flexible sensors and circuit for the Internet of Things (IoT) applications. So before I share my our results, I would like to introduce you to our research activities. So from the PhD and the postdoc studies, we have some of the fundamental technologies such as the CMOS MEMS, neural electronics, and also the nanomaterial printing techniques. So by using this fundamental technology, so we are expanding to the three types of the research topics. The first one is nanomaterials and nano-device physics. And then using the good property of nanomaterials, so we apply to the material, we apply the nanomaterial to the flexible electronics. And then if the device is good, then however, using the lithography, so the device is very expensive whenever we use the evaporator or sputter or photolithographies. So to reduce the device cost, we also applied the technique to the printed electronics, as you can see on the right side of the images. So using that, from nanomaterial to the printed electronics, so we are trying to demonstrate a lot of the applications such as the IoT and also the wearable devices. So today I want to talk about, especially I want to talk about flexible and printed electronics. So for the flexible electronics, so the one of the future for the Internet of Things, IoT, is there are a lot of the applications such as the factory vehicle and the life, human, and also the houses. So to realize this IoT concept, so actually we need to detect a lot of the information from the variety of the surfaces. So without detecting the information from the surfaces, so we cannot realize the IoT concept, even though the internet is very well developed. So to realize the future Internet of Things, so we propose to demonstrate multimodal sensors on a variety of surfaces, including human bodies. So to detect the human body or non-planar surfaces, so the probably flexible and stretchable sensors are good potential good candidate to apply to the IoT concepts. So using the flexible devices, so there are a lot of the application from the medical, nursing, and the condition monitoring, and also the wearable things, and also the industries. So since we are in academia, so we are also trying to find a new field of the flexible devices. So to realize this flexible electronics, the key technology is how to form the active material onto the flexible films. So, so there are a lot of the research and development to realize the flexible sensors and transistors on by using the transfer or printing or deposition technique on the flexible substrates. So there are a lot of the pioneering works on the wearable devices. So as you know, so there are the UC Berkeley or Northwestern University. So Professor Javi and Professor Rogers demonstrate a lot of the wearable flexible sensors and also the stretchable sensors, such as the sweat sensors and also ECG sensors. In addition to that, and also from the Professor Yo demonstrate the SPO, the optical sensor, to detect the heartbeat, like the wearable watch. But they demonstrate the LED and also the photo detector on the flexible substrates. In addition to the sensor, so Professor Kim demonstrated epidermal drug delivery system on the flexible devices. So once we detect something wrong with your healthcare, so this device can deliver to the drug through the skin. So in addition to this practical and also the fundamental research, so Professor Rogers also demonstrated a more practical demonstration. So here, so some the flexible device, wearable patch, is attached onto the baby, and then to monitor the baby's health conditions such as the ECG or SpO2 and also the breathing rate, etc. So since there are a lot of applications, however, so still we think there is a room to develop the flexible devices that is probably the multimodal or multifunctional integration of the sensors onto the flexible films, as you can see this image. So our concept is like the two layers structure. So first layer is a disposable seat. Since this seat can need to be attached onto the human skin, so due to hygiene concerns, so we probably need to be disposable like a bandage. However, to detect the health condition from skin surface, so sensor need to be closer as much as possible to the skin. So that's why we decide to form the sensor onto the disposable seat, such as temperature, ECG, and respiration, perspiration, and also some blood pressure sensors. The reason why we decide to make a two-seat structure is because signal processing and battery cannot be the disposable due to the the cost issues. So that we decide to use a reusable sheet, as you can see this image, and then reusable sheet is integrated with the circuit and also the batteries. So this reusable sheet does not contact to the skin directly, so that we can repeatedly use to the sheet. And then to demonstrate this device technique, so we developed several printing techniques by using mainly inorganic nanomaterials. So since time is very limited, I cannot talk about the detail of the mechanism, but mainly we use a foundry-wash interaction between nanomaterials and flexible films. So the first one is nanowire printing, and second one is the 3-5 ultra-thin film transfer techniques, and the third one is the semiconductor carbon nanotube printing techniques to make random network structures. And the final is screen printing by developing the nanomaterial inks. So after printing or transferring the inorganic nanomaterial films, so we can fabricate a sensor and transistor on the flexible substrates. So first, I want to introduce you the flexible circuits, CMOS circuits. So briefly, I want to introduce you how to make a CMOS circuit on the flexible substrate. So here, actually, I didn't use the printing technique. So I use a lithography technique since we don't have any good technique to deposit the direct insulator layer. So here, first, we use a polymerized substrate, and then we deposit the aluminum as a gate electrode. And then we deposit the aluminum oxide as a gate dielectric materials. And then we use carbon nanotube networks deposition like this networks for the P-type transistors. And next, we deposit the indium gallium zinc oxide using spatter techniques to make N-type transistors. And then finally, actually not finally, but we deposit a source drain electrode over the gold. And then finally, we deposit some of the passivation layer of the polymers over the transistors. So our device structure is like this, the CMOS, fundamental CMOS structures. And then, and also the reason why we deposit the polymer as a passivation layer is to suppress the strain caused by the bending of the device, since this device is flexible transistor circuits. So by adding the passivation layer, so we can reduce the strain up to the 0.08% under the 2.5 meter curvature radius. Of course, if you control more about the thickness, so we can more reduce the tensile strain under such a low bending radius. However, so this is our the state of art in my group right now. And then, so by developing that fabrication technique, so we can fabricate the digital and analog circuit on a polyimide film, as you can see these pictures. So I want to show you the performance of this device. So since here we use a carbon nanotube network on indium gallium zinc oxide, we can demonstrate P-type and N-type transistors. So this is the IDS VGS characteristics. So as you can see, so for the carbon nanotube, we can make some P-type transistors, and also for the indium gallium zinc oxide, we can make an N-type transistor on the flexible substrates. And the field effect mobility is around 10 square centimeter per voltsecond for both the P-type and N-type transistors. So this is, not excellent compared to the silicon electronics. However, on a flexible substrate, this performance at that time, roughly 5 years ago, is quite good for the CMOS circuits. And also, since this is a CMOS circuit, so we also measure the inverter characteristics as you can see on the left side. So based on that, so the performance is good for the CMOS inverter, and also based on this the penetration current, so we can extract the power consumption at the steady state is less than 7 nanowatt per millimeter. That is normalized with the channel width, and also the voltage gain of this the CMOS is around 50s. And then, so since we could demonstrate the CMOS circuit, so we try to integrate more to demonstrate the JK flip-flop digital circuits. So here, I don't remember exactly how how many transistors, but roughly 20 to 30 transistors are integrated onto the flexible substrate to make this JK flip-flop circuit. And the operation is something like this table, and this is the result. So JK and the CLK clock pulse is the input voltage, and the Q is the output voltage. So I cannot follow the each step, but please believe me, the output is operate well as a JK flip flop circuit. So this is before bending, and also even after bending at 5.6 millimeter radius, after 500 times, so still the output behavior doesn't change. That means that our sensor, our circuit can be mechanically flexible without any malfunction of the circuit. So this reliable operation is realized by the passivation layer to reduce the strain under the bending conditions, what I explained at the beginning. And then, so using that technique, so actually we also demonstrate some of the very simple analog circuit. However, so I must skip the result today. So for the chemical, then using the transistor performance, so we wanna try to move to the sensors to use the circuit technology. So here we demonstrate the chemical pH sensors based on the ion sensitive field effect transistors. So basically here, so we measure the pH of the solutions. So this is because pH the solution has a lot of the hydrogen ion depending on the pH values. So hydrogen ion has a positive potential. That means if the solution is deposited over the gate electrode, gate region, actually this hydrogen works as a gate voltage. So that depending on the number of the hydrogen ion, so we can monitor the change of the source drain current change difference. So that's why our device design is something like this. So this we have a source drain and source electrode, and this is the gate region. So we deposit drop the solution over this gate region so that we can see some source drain current change. So this is the result. So when we change the pH value, so as we expect, so depending on the pH value, the current level is changed. Since here we use the N-type transistors, so higher pH value makes the lower drain source current. And then so using that technique, so we apply to the human body to measure the skin sweat pH level in addition to the skin temperatures. So although there are some fluctuation of the output behavior of the pH value right now, however, so we confirm that we could measure the pH of the solution, the sweat, by touching the human skin, as you can see this image, pictures. In addition, so we also integrate the temperature sensor, what I explain later. So this is because the ion sensitive field effector has a temperature dependence. So for the wearable devices, actually the temperature is changed drastically depending on the where you are, like outside or inside of the building. So we also need to measure the temperature to calibrate the output of the pH measurements. So that's why we use the temperature sensor to measure the skin temperature and also to calibrate the ISFETs. So this is the ISFET for the pH sensors. However, so if you are familiar with the electrochemical things, so actually the sensitivity is limited by Nernst theory. So that for the pH at the room temperature is around 60 millivolt per pH. So for the pH measurement, this sensitivity is good enough, high enough. However, for the glucose or other low concentration chemical in the sweat, so this sensitivity limit is sometimes problem to measure the precise monitoring of the chemicals. So to address this challenge, so since I'm from the electrical engineering, so we address the issue using the new sensor structures. So we call Schottky type CCD, charge coupled device sensors. So the main mechanism to detect the pH is the same. So we deposit the pH solution over the gate electrode. However, we have several gate electrodes, as you can see this image. So this is like a transfer of the electron, and then repeat, and then we accumulate the electron to the capacitor several times, so that we can amplify the output voltage. So I will show you some mechanism briefly. So this gate region is some the well of the band. This band diagram. So this gate region is has some well. So this well depth is depending on the pH of the solution or thread. So if the pH is higher, then this gate depth is narrower. And then by turning on this ICG, so this electron can move to the gate region. So this and then we close the ICG so that the electron can be first charged in the gate region, gate wells. So this the number of the electron is depending on the pH values. And then we turn on the TG so that this electron is moved to the capacitors. And then we repeat this process to accumulate more the electron to the capacitor depending on the pH values. And then after reading this capacitance value, voltage electron values, then we remove this electron by turning on the reset voltage of this circuit, so that we can restart the measurement of the pH values. So this is the output behavior of this CCD chemical sensors. So by turning on the ICG, so nothing changed. However, by turning on the TG, so electron is moved to the capacitor, so that output voltage is changed like this step by step. And then by repeating this process, we can increase the output change from this value to this values. And then to more clearly show the advantage of this structure, so this is the output dependent output voltage as a function of the pH values. So by using the standard ISFET, so we can only see this voltage change when you change the pH value of this 2.8 to 11.2. However, by using this the accumulation and transfer techniques, so we can amplify the output behavior like this voltage. So from this results, the sensitivity is roughly 240 millivolts per pH. That is roughly 4 times higher than the conventional ISFETs. And also, of course, by since we integrate the reset functions, so we can also measure the pH value in a real time, like this continuous measurement. And then, so that is a chemical sensor. I would like to also introduce you some of the physical sensors using the printing techniques. So here, first I want to show you the printed strain sensors. So strain sensor consists of the mixture of the carbon nanotubing and also the silver nanoparticle inks. So sensing mechanism is quite simple. So we basically measure the electrical resistance in between the silver nanoparticles. So when we bend the substrate to the downward side, so due to the strain engineering, so we have some tensile strain on these films, so that the distance between silver nanoparticle is increased compared to the flat states. That means electrical resistance should be increased. So this is the experimental result. So as we expected, so when under the tensile strain, so the resistance is increased. And also when we bend to the upward side, so this is so film has a compressive strain. In that case, nanoparticle distance is decreased, so that electrical resistance is decreased. And then based on this experiment, so we could realize relatively high strain sensitivity, about 59% resistance change per Pascal. And also by changing the composition ratio, so we can also tune the sensitivity of the strain sensors without changing the device design. And then I want to move to the printed temperature sensors. So to distinguish the strain and the temperature, so we change the material from the silver nanoparticle to the tin oxide nanoparticles. So sensing mechanism is to utilize the electron hopping at the interface between carbonyl tube and tin oxides. So briefly, so at the room temperature, only few electrons can pass through this barrier due to the low energies. However, at a higher temperature, electron has more energy. That means electron can pass through these barriers more. That correspond to the lower resistance values. So this is experimental results. So as you can see, so at a higher temperature, the resistance is decreased. That is, that makes sense to this mechanism. And temperature sensitivity is around 0.2% resistance change per degree C. So this sensitivity is not actually it's not great compared to the platinum-based flexible temperature sensor. However, so the good advantage is we can make this sensor using only using the printing techniques, so that we don't need any vacuum system to make this sensor. So we can we can increase the device. We can realize the mass production without increasing device cost. And then, so since our focus is to demonstrate healthcare devices, we also want to demonstrate the ECG, the heartbeat sensors. So ECG stands for the electrocardiogram sensor. So this is like the heartbeat monitoring. So for the ECG sensor, so people usually use the gel type electrode. However, gel is some kind of so when we use the wearable device, so we have a high chance to get the sweat. So the gel type sensor swells the sweat. During the sweating process, actually the contact impedance between the skin and the gel is drastically changed, so that it's very hard to measure the ECG under the sweat condition. So to address that problem, so we developed the sticky conductive polymer using the PDMS and carbon nanotube as a conductive polymers. And then, so by developing this device, so we can repeatedly use this sensor up to the 100 times without having any large degradation of the output signal of the ECG. And also, so this is the ECG output before and after exercise with a sweat. So before exercise, we can see clearly see the ECG signal, and then we did the exercise to make us a lot of sweat. So due to the sweat, actually the amplitude of the ECG signal is attenuated. This is probably because sweat increases the contact impedance between the skin and the conductive polymers. However, the advantage is after first we remove this sensor and then just wipe out the sweat from the surface of the skin and the sensor. Then the amplitude of the ECG is returned to the initial value. That means so this material doesn't swell the sweat, so we can easily use the sensor without having any problem about the sweat. And then so this is and also I want to show briefly about the UV sensors. Here we deposit the zinc oxide network, as you can see this SEM image. So since zinc oxide has a large band gap, so we can only absorb the light at less than 390 nanometer wavelengths, so that we can detect the UV light of the sunlight. So some female really want to protect from the sunlight or UV for the UV from the sunlight. So we developed some kind of UV sensors, and then here, so as we expected, so we can see some of the huge resistance change under at the UV region only. Of course, by applying the sunlight, so we can see we can calculate the UV power from this zinc oxide sensors. So that is our fundamental flexible sensors, and then we integrate all the printed flexible sensor onto the disposable sheet as I explained at the beginning, and also at the proof of concept. So we just make some reusable sheet by integrating the carbon nanotube, the transistor, and also UV sensor. And then on the disposable seat, we integrate ECG sensor and the temperature, and also 3-axis acceleration sensor to detect the human motion by using the strain sensor onto the flexible films. And then, so since here we propose the two-seat structure of the two-seat structure. However, even we use a two-layer structure, so we need to make an electrical contact between this reusable and disposable seats. So to make a good and stable electrical contact, we propose to use the liquid metal like eutectic gallium indium. As you can see this image. So since this is a high surface tension, we can make some of the ball of the eutectic gallium indium, so that even after making contact to each seat, so we can make a good electrical contact to the reusable seat. And also, since here we use a liquid metal, so even under bending or moving condition, so we expect to have a good electrical contact without having large noise or disconnectivity between the seats. So this is the experiment result of the connector. So if we use the solid metal contact, actually we can realize very good the electric contact resistance. However, when we bend the substrate, actually with this structure we can see some huge noise of the resistance change difference like this, and also in this structure under the bending radius less than 6 centimeters, so the electrical connection is broken. So to address this problem, so we use the liquid metal. So due to, as I explained, so due to the high surface tension, even under the bending condition, we don't see any large resistance change. And also even under the bending radius 2 centimeters, so we don't have any problem about the broken circuit of the connections. And also using that technique, so the contact resistance is less than 0.1 ohm. So that is probably good enough to monitor, to use the electrical connector. And then, so I also want to show the printed 3-axis acceleration sensors. So to realize this technique, so we learned from the MEMS technology of the resistive-based acceleration sensors. So this is on the PT film. We print the strain sensor onto the number 1 to number 3, and then ground is just silver electrodes. And then we cut the PT substrate using the laser cutters. And then so here it's like a beam structure, and then we put some of the mass on the center of these regions. So this is the FEM simulation result. So when we apply the z-axis acceleration, if you are familiar with the MEMS, so you can easily understand. And the acceleration, so the strain distribution is identical onto the every beams. However, when we apply the y-axis acceleration, number 1 and number 3 has more strain compared to the number 2. So that by monitoring this strain distribution, we can distinguish the direction of the acceleration from x, y, and z. And then, so this is the cross-sectional image of the device. So since to make this the strain distribution, we need a mass. So we attach the acrylic plate of the small acrylic plate onto this center region, so that we, by applying the acceleration, so this beam can easily move. And then this is the experiment result. So once we apply the acceleration, actually this mass, since we have the mass, so this beam is vibrating like this. So the period is around 0.3 seconds. So and then repeat this is used, then we can measure the resistance change. And also depending on the frequency, so we can monitor, successfully monitor the different the acceleration and the speed of the accelerations. And then this is the simultaneous monitoring of the 3 strain sensors. So when we apply the direction, so we can see the strain change for every sensors. And then at the y-axis, so number 1 and the number 3 shows some the spike difference. at the x direction, number 2 shows only the resistance change. So based on that result, so we could successfully fabricate a 3-axis acceleration sensors using the printing technique on the flexible films. And then we attach the device onto the frontier and then monitor the room UV and the skin temperature and the ECG and the motion sensors. So on the picture, actually, there is no wire. However, since we don't have any battery or wire system, so we connect to the sensor to the equipment when we measure the device. And then, so especially in this study, so our main key point is the motion sensor. So if you focus on the motion sensors, so you can see some spike here. So these spikes correspond to the stepping while walking. And also, if you make a strong stepping, so you can see the amplitude difference like this. And also, if you see the resistance change without spikes, this means so people, the human is lying down or sitting up, so that we can also monitor the condition of the human state. And then, so this is so we also developed the wire system to monitor the ECG, skin temperature, and also right now the heart breathing rate. So this is the real-time wire detection. So here this is the skin temperature, and also this is the ECG, and also this is another sensor to show some of the real-time continuous wireless monitoring. And then, so this is the first study of about the flexible and printed wearable devices. That is roughly 4 years ago. And then, so we collect a lot of we found a lot of the problem about the flexible and wearable sensors. That is mainly the stability and the precise monitoring of the health conditions. So especially, so today I want to talk about the skin temperature sensor and respiration and tactile sensors about the stability. So for the first, I want to talk about the effect of the outside temperatures. So here we use the temperature sensor to measure the skin temperatures. So usually for the flexible device community, so we want to make a device as thin as possible. In that case, so we have some temperature sensor on the film, and then we also cover some of the film like this. So here we use the PDMS to cover the sensors. However, if this is for the wearable device, so actually the outside temperature is easily changed, while the skin temperature is almost no change. So this is actually FEM simulation of the temperature distribution through the films. So since we have a temperature sensor here, and the skin temperature is here, so we have some of the temperature difference due to the outside temperatures. And then we decide to make a thicker film of the PDMS here. In that case, we can make a smaller temperature change compared to this very thin temperature sensor. However, this is still that large temperature change. So that's why we decide to make a low thermal conductivity, which is the air, is inserted in between the PDMS and temperature sensor like this. And then we can make a very small temperature difference between the skin and temperature sensors. So that's by making this design engineering, so we can realize the precise monitoring of the skin temperature without affecting the outside temperatures so much. And this is the experimental and FEM result. So this is x-axis is the air cavity thickness here from 0 to the 1.5 millimeter. And then, so when we put the ice onto over these structures, if we don't have any air cavity, so roughly 0.5 to ice cases, we have some 1 to 1.5 degrees difference. That is critical for the wearable device application. However, by inserting the air cavity, so this temperature area is drastically reduced up to the 0.2 degrees C in the case of the ice, roughly 0 degrees C on top. And also, of course, if we use a little bit higher temperature of the higher temperature than the ice, here we use the aluminum plate, 22.4 degrees C, so that the temperature difference is smaller. And also, for the if we use this air cavity structure, so we can reduce the temperature difference, as you can see this result. And then using the sensor, so we attach the device onto the skin with and without PDMS, the air cavities. And then, so we move to the room to the outside of the winter in Japan. So the outside temperature is drastically changed from 26 degrees C to roughly 6 degrees C. And then, so this is the green dot is a commercial infrared sensor to measure the skin temperatures. And then the purple line is the flexible sensor without air cavities. So from this result, actually, you may feel, oh, this is a very small difference. But here, if you look at here, actually, roughly 3 degrees C difference between the skin and the temperature, skin and the temperature sensor output. This is a big difference for the healthcare application. However, by applying the air cavity, so almost no effect from the outside temperature. So we can monitor the skin temperature precisely, even the outside conditions change like this. And then, so that is a temperature sensor to measure the stable and the precise monitoring of the skin. And also, we also study the respiration rate sensors. So this is like a breathing rate sensor. So for the breathing rate sensor, we use stretchable sensors. However, usually when we use the stretchable substrate like a PDMS or silicone rubber-based sensors, even when we move the stomach, so strain is applied too much to the sensor, so that there is some hysteresis or hysteresis problem. That in that case, it's very hard to measure the perspiration rate stably. So to prevent this problem, so we applied some of the Kirigami structure to reduce the strain into the sensors, so that we can monitor the perspiration rate for a long time without having any the fluctuation or large hysteresis problems. So based on that result, we extract the breathing period that is around 4 seconds between each breathing. So that is very standard to the standard adult breathing rates. So based on that result, so by designing the device structure is pretty important for the temperature and also some of the stretchable applications. Here we use the respiration rate sensors. And another application is not a touchable device, but here we also developed the textile-based tactile pressure sensors. So we fabricate a pressure sensor using the old textile materials, and then we apply some of the conductive material on the textile so that we can monitor some tactile pressure, foot pressure distribution, and you can see this the movies. And then actually there is some time delay. This is because of the circuit problem, so program problem. So sensor response itself is very quick, less than 1 second. And then for this tactile pressure sensor, actually, if we want to measure the respiration rate, by using this tactile pressure sensor on your bed, so we can also monitor some the perspiration rate without attaching the device onto human body. However, the resistance change is extremely small, so you need a very good readout circuit if you want to monitor this respiration monitoring. And also, we studied the washing machines washing test. So here we use a standard washing machine. So the one wash is roughly 40 minutes, and also we add the detergent like the standard washing process. So even if we apply this washing process, still sensor itself is not change the output performance. And also we study the long time, also the pressure dependence test. So if we apply very strong pressure, roughly about 1.4 megapascal, so this sensor can be used about 2,000 cycles without any large uh, difference of the resistance output. However, after 2,000 cycles, so resistance value is fluctuating like this. And then also at a lower pressure, applied pressure, so we can use more up to roughly 30,000 cycles. And then so we plot some of the threshold cycle as a function of the applied force. So this is kind of the log scale, but this is a kind of the linear fitting like this. So for this application, if you want to use a foot pressure monitoring, so the maximum pressure is about this region, so that you can use roughly the 4,000 or 5,000 times. So that is roughly 1 or 2 days use if you apply this sensor on your shoes. And for the bed application, actually the body pressure is about 5 to 10 kilopascal. So in that case, we can use more than 100,000 cycles on the bed to detect the human motion and also the pressure over the human bodies. And then so this is the fundamental study and also the reliability and precise detection of the sensors. And then I want to move to the other applications. So first, here today I want to talk about robotics and airflow mapping and also plant monitoring. So first is the electronic whisker array. We call the e-whiskers. So that can be applied to some kind of the very small size of the robot. So even this small size of the robot needs multiple sensing functionality to detect the environmental conditions and also the targeted information. So to realize that, so we use the strain sensor onto the PET film, and then we make some kind of this structure, com structures, and then we scan some 3D objects. So here, since I'm from the Osaka Prefecture University, we use the initial of the university, and then we scan the e-whisker over this structure, and then this is the output result. So although the resolution is not so great, but still you can see some OPU object. And also by laminating the temperature sensor with this strain sensor, and then scan some of the hot metal plate. So we can also monitor the strain and also temperature distribution simultaneously, as you can see this result. So this is the e-whisker, and also for the robotic application. So many people think so e-skin. So here, so we also developed the e-skin integrate with the soft robotics. So this is the air pressure based pneumatic soft actuator to make the robot hand. So this soft robot can hold some of the object, but since the air pressure is not so high, so it's very hard to hold the heavy things. But still we can hold the ball or some object with this structure. And also you cannot see, but this soft robot has actually the tactile and temperature sensor onto the tip of this sensors. And then this is the output signal. And this is the experimental result. So when we apply to some hot object to the soft robot, so sensor, the temperature sensor detects some object temperature. As you can see, this the curve change. And also, since this soft robot holds some object, number 3 and number 4 shows some tactile detections. And then once we remove the object from the hand, so drastically the force is returned to the 0. And also the temperature is gradually decreased to the original value. So this slow response of temperature is because we use a PDMS. So temperature is slowly applying or removing from the the material, so that the response is very slow. But still, you can see some of the difference of the temperature detection, temperature sensor. And also good things. So here we have actually 4 strain sensor like this, and the center is the temperature sensors. The good thing to integrate the multiple tactile sensor is we can also monitor the slipping of some object. So actually we try to apply the slipping object like this. So this is the result I show you at the previous slide. And then we zoom in this region. That is the result is like this. So actually from at the beginning, so we have some tactile force on the number 4, and we sliding the object. The tactile force is moving to number 4 to number 2, so that we can monitor the tactile pressure movement from this result. So this time difference is about very small, but still we can monitor some of the time difference. So this can be the robot can also know the slipping of the object by monitoring the time difference of the tactile force change. So right now, so we cannot integrate the system, but by using the function, so we can also feedback the signal to the robot to change the tactile force to hold the object without dropping. So that is our soft robot and soft robot or robotic applications. And then quickly show the airflow mapping and also so here, so we use the printed temperature sensors. So and also we print some of the heater in the center of the film, and we have 2 temperature sensors. And then by applying the heater turned on, so you have some of the temperature distribution. And then if you have some airflow from left to right side, so this temperature distribution is changed to like this. And this is the FEM simulation. So at the flow rate 0 meter per second, that means without any airflow. So you can see the identical heat distribution. However, under the airflow, so this heat distribution will be changed to like this. So left side is almost room temperature, and the right side has some of the heater effect. So by monitoring this, the temperature change using the temperature sensor, we can also detect the airflow detections. So this is the experimental results. Actually, when we change the airflow, so we can see some temperature difference from 0 meter second to the 1.5 meter per second. And also, depending on object, actually, when you use a metal object, actually, it's very hard to measure the flow rate without having the air gap like this here. This is because what I explained at the wearable device of the temperature sensors. And then this is the IR sensor. When we apply the airflow, so some tail of the temperature change is observed. So this is because of the airflow of the airflow direction. So and then we integrate the 8 temperature sensor, and this is the heaters. And then this is the experiment result. So when we apply the airflow to number T1, the case, the T5 has higher temperature difference, while other sensors show almost no temperature difference. And then of course, by changing the direction of the airflow, so you can see the maximum temperature position will be changed. So based on that result, so we can use this platform to monitor the airflow of the object. And then we integrate some of the strain, this flow sensor onto the curved structures. And then when we flow this direction, and then as we expected, so this left 2 and the center 2 sensor show some of the similar direction of the air to this left to right side. However, when you look at this side, so this side shows some of the random flow direction of the temperature sensor. This is because the turbulence is happen at this end of the regions. So using that flexible flow sensor sheet can also monitor this turbulence of the airflows. And then I will move to the plant monitoring. So here, so we also developed the humidity and the light optical sensors, as you can see this image. And so we also put the temperature sensor on this. And then by attaching the device onto the leaf of the plant, so we can monitor the environmental humidity, temperature, and the sunlight. And also we can monitor the, the, the what's called the dehydration or the breathing of the leaf of the plant. And then to make the humidity sensor, we decided to use the zinc indium sulfide nanosheet stacking layer. As you can see this SEM image. And then by changing the humidity, so resistance is changed like this. And we also confirm that this material showed good stability up to 2 weeks or something without changing large degradation or something. And also this sensor doesn't have a temperature dependence. This is a temperature change. However, resistance of the humidity sensor is very small, so that we can monitor the humidity individually, even under the temperature condition change. And then we apply this sensor onto the leaf of the plant, and then due to the biological things, so under daytime, so this region is open to make a change of the hydrogen oxide. So that using the humidity sensor, we can monitor this hydrogen oxide. And then so we attach a device like this, and then we apply under the light, so we can see some of the humidity distribution like this. However, under the dark state, similar to the night condition, so the humidity level is almost nothing. And then again, we apply the sunlight, then we can see some of the humidity distribution on the front. And then finally, we put the device onto the plant and also monitor the long time, roughly 2 weeks monitoring of the humidity and temperature and opticals. So 12 hours light on and 12 hours light off, so to imitate the daytime and night times. And then at the daytime, actually you can see some of the humidity response on the leaf. And then interestingly, actually, after 8 or 9 days, actually, this peak is disappeared like this. This is most likely because the dehydration state of the plant, since we didn't apply any water to the plant. And then here we apply the water to the plant, then the humidity level return to the original. And also here we can monitor the lamp and also the room humidity and room temperature as well. And then that is our activity. Actually, we are also working on the feedback system with a multimodal wireless health condition censorship. But since this work is still under submission, so I cannot share the result today. But hopefully at some other conference like MEMS or other MRS or some other conference, I will show you the state of art result of the feedback system with flexible censorship. And then that is my talk. So for the future Internet of Things applications, so we need multimodal sensors, but probably to detect a variety of the surface, including human or non-planar surfaces. So we need to use the flexible sensors with multi-functionalities. So we are now working on to apply this multimodal flexible sensor to detect a lot of the information. And also we are now working on the feedback and also the system integration systems to use the practical application. And then this is the acknowledgement. So the result I presented today is mainly done by the Dr. Kai-Chen Shu and also Mr. Yu-Yao Liu and also the Mr. Yusuke Fujita and Ms. Satoko Honda and also alumni studies. So I really appreciate their contribution and also the effort on the works. And also this some part is collaborate with the National University of Singapore and the Mongolian University and also the JAXA in Japan. And so this research is funded by this research fund in Japan. And finally, I would like to advertise the opening. So we are now looking for the one postdoc fellow with a background of chemistry or material science, starting from January 2021 or later. So it depending on the visa issue. So since now the visa is controlled due to the COVID-19 virus. So anyway, if you are interested in the position, so please email me. So this email address. And then, so that is my talk. So thank you for your attention.
Okay, what a nice talk. Yeah, so we really enjoy your talk very much, and so you are so kind. You still have, openings for the students. That's the best offer. I think, many students was here, they can, apply for this position. Yeah, because now COVID-19 get many places was shut down. So they don't have a lot of openings. So thank you, Kenny. Yeah, many questions for you. So I just pick up a few of them. Yeah.
Yes.
The first question is for flexible circuit or sensor. Since they are multi-layer, could you give the comments that how is interface stability?
Interface stability
Yes.
of the circuit?
You see that for the flexible circuit, all sensors are normally multi-layers.
Yes, yes. Okay, so circuit means the sensor also. So
Yes.
basically here, so we apply usually we test the 1,000 to the 10,000 the bending test. So always we apply the passivation rate to reduce the strain under the bending condition, so that we can reduce we can we can suppress the strain into the sensing material or transistor materials, so that we can make a very stable the flexible sensor and transistors. Is that answer?
For the interface?
Interface. So of the nanomaterial onto the flexible substrate?
For these different layers. Yeah.
So we didn't study so much about the interface between each layers, but based on the result, we don't see any sensor degradation or transistor degradation. That means probably interface is quite good and stable. And also for the transistor application, we usually use the polymer deposited by the spin coater or something, so that the interface is pretty good adhesion.
Okay, that's very good. I think this is based on the materials you choose. If you choose the materials more, stable, should be better.
Oh, yeah, sure.
Yeah. Okay, next question is pretty long. Okay. What are the advantage and disadvantage of the print acceleration sensor as compared to the flexible sensor based on the conventional fab technique? What is minimize the feature size of the print electronics you can achieve? Yeah.
Okay, so good point. Actually, for the acceleration sensors, so compared to the conventional MEMS acceleration sensors, so if you use only one acceleration sensor, I cannot find any good advantage, actually, to be honest. So since our technique, so we need to use the film, and also we need to make some of the structures. So we cannot use the lithography technique, so that the device size is quite large, actually. So the minimum size is roughly 5 millimeter size squared. So if you want to use one acceleration sensor, actually I recommend to use MEMS-based acceleration sensor. But if you want to detect the acceleration distribution, like if you attach the device onto the bridge or the infrastructure on the large scale, so since here we can make a device sensor using the printing techniques, so we can easily integrate a lot of the acceleration sensor on the film with relatively large films. So probably for the IoT application, we may be able to find some good advantage to use this printed acceleration sensor. But for the wearable device, for sure, we shouldn't use this printed sensor. This is just demonstration for the proof of concept.
Okay, just listen to that part. I think you will take off many maps people's job, right? Yeah,
Yeah,
so that
right.
should be a big battle. So now you give the very good answer. Yeah. So what's minimal size? Yeah, for the printed electronics you can achieve.
Actually, so here, so in my group, so we mainly use screen printing. So the line width of the pattern is about zero point 0.2 millimeter, 200 micrometers. But if you want to make a smaller, so you can also use an inkjet printer. So that can realize probably less than 10 micrometer, but but of course more than micrometer. So that is a minimum, I think, resolution right now, so people can
Okay,
realize.
yeah, that's good. Many use printing, to make electronics, and now is going achieve very high resolutions. Yeah, I think that's coming. Yeah. Okay, next question. Many electrochemical sensors suffer from stability and lifetime issues. Have you done any prolonged tests to verify the stability and lifetime?
Yeah, so that is also a good point. Probably this guy knows well about the chemical sensors. So, so yeah, right. So
I know you well.
so Drift is program to monitor the chemical using the printed and probably not flexible, flexible sensors. So right now, so we are now working on the stability of the chemical sensors. So I cannot talk about details now since we are still working on, but by changing the material and also sensing mechanism, we found that so we can make some relatively stable monitoring. So we test the chemical detection for the roughly 1 day, 24 hours, but still we don't see any degradation or drift effect using that techniques. So it's coming soon. So, but now I cannot talk about the details. But probably there is another a lot of the technique to make a stable chemical sensor.
Okay, I have one question following here. So how you do the calibration?
Calibration.
Yes.
Okay, so the result I present today, always we test the what's called reference solution to check the baseline, and then we measure the sweat or mainly sweat here, and then we use the value to change to calculate the pH value of the sweat. So always we need to calibrate using the reference solutions. That is kind of the problem for the chemical sensors. So this is corresponding to the stability.
Okay, cool. Yeah. So next question is for print stream and temperature sensor. How can you guarantee the reproducibility of the printing process? And how about its commercialization?
Okay, so here, so we use the screen printing for the screen sensors. That case, I didn't, I couldn't show you the histogram of the sensitivity distribution, but it's not too bad. Even though we are making in the university, but for the commercialization, of course, we need to, we need to make the what's called reproducibility almost perfectly. So that one is I cannot answer right now. It's very hard to study the reproducibility from the university. But if someone is interested, we want transfer the technique to the company or something to make reproducibility and also mass production. Right now, it's not perfect, but it's not too bad compared to the yeah, it's not too bad. Yeah.
Okay, so I know Osaka is a place full of the, calibration of industry. So did you have a collaboration with them to push for the commercialization?
Oh yeah, of course, yeah. Always we calibrate the sensor because some the base resistance also is slightly changed batch to batch, so we need to calibrate the sensor every time. So that is kind of the annoying process actually.
Okay, I see. I'll go to the last question. For the sticky conducting polymer, is it biocompatible with the skin? And how to avoid the environmental parameters effect?
So for the biocompatibility, so here we use a carbon nanotube and PDMS, silicon rubber. So most likely it should be fine for the human body. However, since we have the solid film, so sometimes we have a problem with skin, like itchy or something. So in that case, but we couldn't study the long time biocompatibility using the human skin. So I cannot say this is perfect, but material itself should be the safe for the human skin. And so how to avoid the environmental parameters?
Okay,
I'm
can you
not
see
sure
that?
about environmental parameters. Mean the temperature or something?
Yeah, something like that. Always asking for the, humidity and the temperature and the other changes.
So humidity, actually, so this polymer is in between the film and the skin. So usually when we use this polymer, so polymer itself is not exposed to the environmental condition directly. So you don't see any big effect of the environmental change. But I'm not sure. We didn't study about temperature or humidity part. So we studied the sweat test. So that is probably becomes similar effect. So amplitude is the attenuated because of the interface between skin and the polymer. But I don't know exactly how much effect this material has.
Okay, cool. We still have other questions, but I will send to you later. Okay?
Okay.
Yeah. Now I see all of us here. We need to go to. Oh, yeah. Sorry. Before that, I need to deliver this certification to you. I can act that's as normal. Yeah, we deliver the certification to the wonderful speakers. So, Kenny, you use your wonderful technology to connect the world and the universe. That's all for you.
All right, thank you then.
Okay, I will give you the hard copy later when we met. Okay, I hope in the near future, not that too far. Yeah. Okay, yeah. We go to this dialogue part. Yeah, so we got everyone here. Yeah, also Paul, yeah, maybe need some time to wake up. Yeah, he go to bed really late. He sent many emails. Yeah. Okay, yeah, so welcome everyone. Kenny just gave talk. Yihui was from Tsinghua, was already there. Professor Saif Rahman and the team. Yeah, welcome. So first, like normal, I want to ask some questions to our speakers and our distinguished guests. Just now we listened to Kenny's talk. We see that the young generation was grow up so fast and doing so well. On this stage, I see, three of you are very, very outstanding, in your age. I want to know the secret. Yeah, like Kenny, maybe you go first. Because normally I heard many stories like in Japan, as a very well developed country, many young generation don't want to go to science. Yeah, why you stick with science and you do so good? Like you got a lot of jobs done. Yeah.
It's a hard question, actually.
Yeah, it is. I changed my mind.
So I don't know exact answer, but right now, so people think Japan is good, but right now, so young generation is worried about the situation of the science and technology because now the China and the Korea and some of the Asia country developed very well, and also
we're developing, you developed. That's a big difference.
I mean, you already catch up the Japanese technology and some probably already overcome the techniques, and then so you are maybe the better position than the Japanese techniques. So we are also worried about that point. So that's why we try to study and develop the technology hardly again, but it's very hard. So since Japanese is very shy, so
no, I don't think so.
they don't want to go outside to study in the US or in the other Asia country or Europe. So that is one of the problems to make a good international community and the collaboration. So that needs to be, I think, addressed in the near future.
But you're doing very well. Yeah, you're not only get very good results, you also get very good connection. And you study in US and get a lot of friends. Yeah. Actually, just now the most hard question came from your lab mates in US. The one who know you very well. Okay, yeah. So we came to Yihui. Okay, Yihui. You're from Tsinghua University. I'm from Peking University. That's always a competitor. Okay. Yeah. And your last name was Zhang. My last name was Zhang too, right? Yeah. I want to ask you a question is like, you get a good training in China and you also get some training in US, like, Kenny got some good connections with different peoples in different areas. So what kind of benefit you take, from the last 10 years for you grow up to be a new star? Yeah.
Yeah, that's a very good question. I think in both China and the US, I got different types of trainings. And actually, some of them are very similar to each other, such as the logical thinking, the critical thinking, and how to identify important problems, and how to appreciate the importance and the significance of the good research. So I think many of them are very similar because I obtained my PhD in Tsinghua University, and after that I moved to US to Northwestern University to do a postdoc. So I think, in Tsinghua, I also got very good training in the fundamental aspects of doing a good research. And also, I think there are indeed some difference. And for example, I think the research direction which I did my research on in the US is one of the most emerging technologies regarded on the biomedical devices. And when I have an opportunity to work in that top research group, I really have a very good connection to the most top to the top research. And of course, in that period, I got an opportunity to figure out a new research direction. That is the mechanics guided 3D assembly, and I continued that research direction when I returned to Tsinghua, and this has already become an important research direction in my group now. I think, yeah.
That's very good. Yes, from different side and different areas, you training and get advantage, right? Yeah, and then eventually, go ahead to find your own, direction and working on that. So yeah, my next question should be for Tim Zhang. Yeah, so it's my Thomas. Yeah, we're all from Henan province, but he's doing much better than me. So I always think, Tim, yeah, you are a supermodel. So yeah, could you say something for your training background and what you get the benefit?
Yeah, first of all, I think Alice, you ask a philosophy questions.
Philosophy.
When there's three important questions. One is who I am, and second is where I'm from, right? And the third one is where I will go. I think that most important is that make sure where you will go to that direction. I also, like Yihui, I got my basic study and background in China, and I got my PhD in US, and I returned to China and worked for about 10 years. I think I always make sure where I will go so that I will have the very specific objectives. That is very important. And I think for most young students and also the researchers, it's very important that to make sure that after 5 years and what kind of the person you will be. Because in the internet age and we got too much information inside our head. Sometimes at a young age, it's hard for us to make the right decision and good decisions. And it have to be make sure where you will go. I think that's very important.
But the serious thing, you stay, many years in US, and then you didn't get your head messed up, right? What did they teach you that time?
Well, I think I learned a lot from my PhD time and also my working early career in the United States. Be more creative and be more diligent. And at the early stage of our career, I think also it's very important to have a good habit to always to find the innovative ideas and from the novel ideas for our research directions. And also persistence, I think is very important. Once you decide what kind of person you will be after 5 years, just insist on it. So I think Alice asked a very good philosophy questions.
Okay, thank you very much. Actually, this came to Professor Raman. We are so proud you be here, and we know, you are very famous in the part for electrical power area, and done a lot of nice work here. But today, I really have a question for you. Is in last 40 years, maybe in your career, you must host a lot of students from a different area, right? Different country, and did you find the difference and how you training them, to come to a good direction or good career? Yeah. Okay, that's for you.
Very good question, Alice. I have been teaching for, as you said, more than 40 years now.
Oh, 40.
So I have processed maybe more than 2,000 applications personally myself, and I have given 70 PhDs and 60 some master's degrees. The point is the following. I get applications from China, India, Europe, North America, Africa all the time. I have now some category in my mind. I have right now one from Tsinghua University, my student, and I finished one from Tsinghua last year. So point is, when they come to me, I ask them this question, why are you here? Is it because you want to come to America, or you have some other intellectual curiosity that you want to advance? And I push them in that direction, that learn something new. And I have one saying, do not repeat what you hear. You have 2 ears, 1 head. Hear it, process it, and then take it out. Do not repeat what you hear. Process it. My focus is make them think, so they know why they are doing things. I said 3 things. When something you see, the 3 happens. One is what happened, how it happened, and why it happened.
Mm-hmm.
Most people don't ask the why part. Yeah, what happened? I see it. I saw this happening. Why is the more important part? So when they finish their degree with me, they write, Virginia Tech is a rule in the dissertation document, 1 page called acknowledgement. They acknowledge people they have been closely connected with. They talk about their mother, father, sometimes husband, wife, sometimes their lab partners. For me, they always say, he made me think differently. That's my achievement, that I can make you think differently. Then you go out and you are an independent person on your own. That is my philosophy in dealing with all the students from all over the world. I hope that answers your question.
Yeah, that's very good. That's a very good point. Actually, yeah, that's, I need to say that we have a lot of audience, very large number of audience. Like just now was already over 300,000 audience there. Many of them are the graduate students or some even, senior in the college. So they are going to, fighting for the future, where to go, right? And what kind of direction, what do you want to learn, and what kind of, the really future you want to have. I think that you give a very good answers for the people. So yeah, you need to think more about that and go on that. Yeah. So now the last question for the, three young scientists is, yeah. So what kind of students you want to pick? Yeah, like Professor Norman already said that. What kind of student you want to pick? So Tim, you can go the first. Yeah, because you have a lot of nice students.
Thank you. Yeah, I think three were maybe the diligent is the first, and also creative, and also happy maybe because
Okay.
they face many challenges. I want to make them happy,
Okay, that's very good. That's a happy group. Okay, yeah. So Kenny,
Yes. So, I,
want someone handsome as you?
no. So I think the most important part is creativity. So if the student has a creativity, so we can do anything. And so the student future is also promising. So I think that is the most important part. So I will take a good creativity guy.
Okay, so in the audience, please remember these words when you apply for Kenny's opening that position. You must show you are very creative. Yeah, you have some new ideas. Yeah. Okay, Yihui. Yeah, how about you?
Okay, so in terms of the selection criteria for PhD students, I would usually consider three aspects. So firstly, I would pay attention to the passion of the students on the research direction of my group. So being passionate, the students are more possible to overcome the difficulties and challenges in their research. And secondly, the motivation is also very important to consider, especially the PhD students usually need to study for around 5 years. So self-motivated students usually have a stronger determination and perseverance to get through the PhD study. And lastly, I think I would prefer to choose students who are more open-minded and easy to communicate. So these are essential for interdisciplinary studies because they need to learn many new things and collaborate with different groups. So these are the three aspects I would consider.
Okay, very good. I like the last, characters, open and, calibration. Yeah, we have to. Now is your word. Everyone should, pay attention to others and, working hands by hands. And this was why Professor Raman here. Yeah, Professor Raman is going to take a big job, right, to help all the scientists from the whole world and to get everyone collaborated together. And now, Professor Raman, you ready to say for your election? Yeah, how you to enhance all this collaboration and all this kind of open mind. I think that's the time, we should enhance on this, emphasis on this. Okay, yeah, please, Professor Raman, now is your time. Yeah. Okay, please share your screen. Yeah.
My screen, yes.
Yeah.
Give me a second.
Okay, cool. Good. Yeah,
I'm
come.
going to pick it up 1 second.
Yeah, okay. The first page, please.
Okay, I'm here.
Yeah.
Good. As Alice said, I'm a candidate for IEEE President 2021 elect. Election is going on right now. If you see at the bottom of my screen, vote at IEEE.org/elections. If you go there anytime between now and October 1st, you can vote for anybody you like. I hope you do it for me, first of all. Second is, I have been in this business of education and IEEE for more than 40 years now. So I have seen IEEE from different perspectives. I'll share some with you so that you understand where I'm coming from. I was born in Bangladesh, not far from China. I went to US almost 45 years ago. I have been working in many countries, China included. So I've seen the world from different perspectives. That is how I want to present myself. This is how I see IEEE's challenge today. IEEE is a big society, as you know, many of you, with more than 400,000 members globally. China has about more than 20,000 members of IEEE, 20,000 members of IEEE. This is a big number. When I talk to my friends in China, India, many other countries, they ask this question: is IEEE American society because all Americans are running it for a long time? Or is a global society headquartered in US? It has to have one headquarter. That's the US headquarter. What is it? The way I see it, it's a global society, happens to be US headquartered. That's how I see it. But then the question is, then if that's the case, we must treat all members the same way. This is the challenge I have, and I want to work on this. Sometimes based on legal issues, other issues, IEEE sends a wrong message to the membership, which is wrong. For example, IEEE is a membership organization. Membership is not a company, right? It's not a government agency, it's a membership. All the members make IEEE possible. That's not done. If that's the case, we have to deal with an American, Chinese, African, European, Australian